So let's get into another example so that we can see it all the way through from start to finish and bring in StatKey and see how it is that we can get the results we need from software. We're looking at home prices in New Jersey, New York, Pennsylvania, and California, and we're going to address the question of whether mean home price differs among these four states. So, first, just looking at our summary statistics, it does look like the smallest being 249 and the largest being 715. There's a very good chance that we're going to find statistical significance here. It does look like average home prices differ. So the question that we're really going into is this the kind of difference that you might just see by luck of the draw? If I were to draw a random sample of 30 houses from California and a random sample of 30 houses from another state, I wouldn't expect the mean home price to be exactly the same. Is this just that difference that's due to randomness, or is this a statistically significant difference which could not be attributed to random luck? Our hypotheses are always pretty much the same for ANOVA. It's that all four means in this case are equal, so mu sub New Jersey equals mu sub New York, which in turn equals mu sub Pennsylvania and is equal to mu sub California. And my alternative hypothesis I can phrase one of two ways. I can say mu sub I is not equal to mu sub j for some pair ij. Or I can phrase it as at least one pair of means is different. So the first thing we're going to do is check conditions for using an F distribution. And to do that, we need to really look at the samples. And that's going to be going all the way back to where we started in StatKey, which is descriptive statistics. So first we're going to descriptive statistics, one quantitative and one categorical variable. We're going to upload the file homes for sale, which is a lock data set. So in StatKey, descriptive statistics and graphs, one quantitative and one categorical variable. The categorical variable defines the groups, and we're comparing means over the one quantitative variable in each of these groups. So upload file, and I'm going to sort these by name to make it easier to find. Homes for sale, we don't want them isolated, just the homesforsale.csv is the correct one. And we are looking at price by state. So here we have comparative dot plots. We could also look at histograms if we find those a bit easier to look at, and we can look at box plots. It does look like we have a pretty extreme outlier in California. We have several outliers in New York as well. Any of these might be some concern. We do have n equals 30 for each group, but this extreme outlier here I think is still some cause for concern. So these extreme outliers are some cause for concern. We're not sure about the normality condition. We would perhaps proceed with caution on this. Let's check also the equal variance condition. Coming back to StatKey, we want to look at standard deviation for that. Here's our four standard deviations. The smallest is 179. The largest is 1112. So this equal variance condition is definitely not met. The smallest is about 179. The largest is about 1112, much more than twice the smallest, right? Remember, it's okay to have a factor of 2 in there, but maybe not a factor of, this looks more like 6, a factor of about 6. So none of these conditions are actually met. We're going to go ahead and proceed anyway, just so that we get through the whole test. So back in StatKey, I'm going to go to the home page again, and under more advanced randomization tests, this one called ANOVA for difference in means is where we want to go. We don't do ANOVA for regression in this course. We're going to do ANOVA for difference in means. And I need to upload that file again. Actually, let's see. Yeah, it already is uploaded, so I can just hit change columns, and it allows me to come back and just select those columns again. It goes to the most recently uploaded file if you do that. So I have my same data set in here. And from this page, the main thing that I want to take away is the F statistic, which is right in there in the original sample. F is equal to 2.747. So F equals 2.747. And I'll figure out my degrees of freedom in order to generate a graph. My numerator degrees of freedom is the number of groups minus 1. We had 4 groups, and therefore my degrees of freedom for the numerator is 3. And for the denominator, I want my total pooled sample size. 4 groups of 30 each is 120 data values total. I'm going to subtract off the number of groups from that. So 120 minus 4 gets me 116 for my denominator degrees of freedom. That means that I would want to go to StatKey again, back to the home page, now to theoretical distributions F to get this F distribution, and type in those 2 degrees of freedom values, 3 for the numerator, 116 for the denominator. And that gets me this curve here, which looks an awful lot like the one that we have printed in our handout. So that one is already generated with the correct degrees of freedom. Let's try to estimate our p-value from this. Our F statistic is 2.747, which is right about here. And so my tail area then is going to start there and go off to the right. Now, looking at this, we want to estimate a p-value in order to get some practice at this. Our estimate of this p-value from the graph, I would start with, does it look like more than 10%? And I would say no to that. Does it look like more than 5%? Maybe. So I think this p-value looks like it's between 0.05 and 0.10. So I would give this moderate significance but not strong. So moderate evidence but not strong evidence of a difference. Let's see what StatKey says the p-value is. If I do right tail, down here it says 3.231. That's the boundary of the 2.5% tail. I'm going to overwrite that with my p-value, I'm sorry, with my F statistic of 2.747. And this gets me 0.046. So it looks like my guess was a little bit off. It's actually less than 0.05. But it's good to get this practice and kind of readjust, right? Now let's go ahead and write our conclusion based on the 0.046. So part 1 is what level of evidence do we have? What strength of evidence? And I would call this just barely strong evidence. We have strong evidence of a difference in mean home value among the 4 states. Or mean home price among the 4 states. And in part 2, where do we observe that difference the most? Definitely we saw the highest prices in California. And we saw the lowest prices in Pennsylvania. So given that we know there's a difference, we can certainly conclude there's a difference between the highest and the lowest. Beyond that, it's hard to say whether there really is still a statistically significant difference between California and New York, between New York and New Jersey, or between New Jersey and Pennsylvania. Any other pair we'd have to look at individually in order to say for certain. I'm going to come back to StatKey just for a moment. Since our conditions for using the F distribution weren't met, I'm back on the ANOVA for a difference in means page. If I generate a few thousand samples here to get a nice approximate F distribution that's not really the theoretical distribution, but just using a resampling technique, now if I hit right tail and overwrite this with my F statistic of 2.747, it looks like the p-value is a little bit smaller using this randomization technique, 0.028. Perhaps the difference in these two p-values is because our conditions weren't really met for using an F distribution. It did seem like from just looking at these sample means, we should have probably seen maybe stronger evidence than we saw of a difference in means. These numbers vary quite a bit, although the standard deviations are also pretty big, and that could explain why we didn't see stronger evidence than what we saw. In any case, keep in mind when we do an ANOVA, we're using an F distribution. We're comparing means, so we have one quantitative and one categorical variable, where we're taking means of the quantitative variable and using the categorical variable to define the groups over which we are calculating those means. This is a multiple comparison test, and therefore we have a two-part conclusion always implied in any multiple comparison test.